Okay, in this video we will continue the discussion of how to solve for the Poschl-Teller potential, this time using a different method which is called matrix diagonalization using the harmonic oscillator basis functions. We will discuss about what all these mean. So I wrote here that in quantum mechanics in general we want to solve the Schrödinger equation. Here this is the one-dimensional Schrödinger equation. And okay, for the Poschl-Teller potential, we got lucky and there are analytic solutions. But in the general case, the potential, so in general, V of x might be some complicated function such as V of x equal to the hyperbolic secant squared of x plus maybe x squared minus e to the minus x squared plus dot dot dot. Okay, this is a crazy potential. It doesn't happen, but I'm just trying to give you the idea that not all potentials are exactly solvable, and some potentials are so complicated that we need to resort to other methods to solve this differential equation. Okay, I hope this makes sense. So in general, okay, we wrote this potential, thus analytical solutions might not exist. Sorry. And in most cases, they don't exist. Okay, so what do you do? So what do we do? Okay, so the solution is to use known complete sets of functions to expand the unknown wave function. That is, we expand psi of x, the wave function that we are trying to find, in an expansion that goes from 1 to infinity of some coefficients that we need to find times psi of n of x, and where psi n of x are square integrable functions, as we will see. Which means that the integral from minus infinity to plus infinity of yn of x, ym of x dx is delta n m. Okay, so these are orthonormal. Okay, and this integral exists. Okay, if they were not square integrable, this integral will be infinite. Okay, what else do I want to say? Okay, notice here that the expansion goes to infinity. This is impractical. We cannot calculate things to infinity, right? So we usually use a cutoff. So in practice, we use a cutoff for the wave function, or psi of x goes from 1 to some n max cn psi of n of x. Okay, and we need to have converged results to determine this cutoff, and we will see what this means when we go and see the code. Okay, so for now we will just do the theory. The reason why this works is the variational principle. So I'm not going to discuss it, I'm just going to quote it here. So the variational principle guarantees that any trial wave function will have a ground state energy that's larger than or at least equal to the actual ground state of the problem. Okay, so expanding in any complete basis will converge to the exact result from above. And I'm gonna write one more thing. Expanding in a basis is mathematically equivalent to finding the eigenvalues and eigenfunctions of the Hamiltonian matrix in the basis of choice. Okay, I wrote too many things. Let's take a step back. Again, we want to solve the Schrödinger equation, which in units of h equal to m equal to 1 is written as minus 1/2 double prime x plus v of x psi of x equals e times psi of x. Okay? Now the Hamiltonian is this part, minus 1/2 d squared over dx squared, okay, which is, this is the kinetic energy operator, okay, plus v of x, okay. I hope this makes sense. And the Hamiltonian matrix now is written as, let me see, is there anything else I want to say here? And we said we are going to expand in a complete basis. Psi of x is equal to psi of n from n equal to 1 all the way to infinity of cn of x. Okay. Now the Hamiltonian matrix has matrix elements nu and m, which are given by this expression n h m. Okay, so the Hamiltonian matrix looks like this. I will talk about all this, I promise. So 0 h 0 and then 0 h 1 dot 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 0 h n. Okay, so this is the matrix. Then this is 1 h 0 1 h 1, okay, and here is 1 h n, and by the way, this n should be n max. Okay, remember that we use a cutoff in our wave function, so this element here is going to be m h 0, okay, and this is also n max. And finally, this element here is going to be n, h, n, and n is equal to n max. Okay, and this n max corresponds to this n max of the wave function. Okay, now what are all these? Okay, we said we will use the harmonic oscillator basis functions, and this is the time where we have to discuss about them. So Cn of so this quantity n is called a ket. This is using Dirac's notation for simplicity. This is just Cn of x, and Cn of x are the solutions to the harmonic oscillator problem. And the harmonic oscillator potential is simply 1/2 m omega squared x squared. Okay, I'm gonna erase this for now. And I'm gonna quote the wave functions that look like this: 1 over the square root of 2 to the n factorial times m omega over pi h bar to the 1/4 times e to the minus m omega squared x squared over 2h bar times hn of the square root of m omega over h bar x, where these are called the Hermite polynomials. Okay, and n goes from 0, 1, 2, all the way to infinity, but in our case, as we said, we will go all the way up to n max, and we'll see that in the code. Okay, so for example, the state 0 is the ground state, and if we plug n into this expression, we have 2 to the 0 is 1, and 0 factorial is 1, so that expression is 1. So we need this m omega over pi h bar to the 1/4 times e to the minus m omega squared x squared over 2h. Okay, and the Hermite polynomials of order 0 are just a constant 1. Okay, so this is the 0th state. Okay, the ground state. Okay, now these functions, so these Cn's of x, okay, are solutions to this differential equation for the harmonic oscillator: minus j squared over 2m d squared psi over dx squared plus 1/2 m omega squared x squared Cn. I forgot the n down there, and this is equal to En Cn, with En being the energies or the eigenvalues of the harmonic oscillator given by n plus 1/2 h bar omega. Okay, so there is an equal spacing between the eigenvalues of the harmonic oscillator. Okay, one more thing I want to discuss before we go back to our problem. So to summarize, we haven't done anything yet, guys, pretty much, sorry. So we want to solve this equation. Then we say here that v of x might be some complicated function of the position, okay? In which case analytical solutions do not exist. So what we do is to expand our wave function into this basis over here, okay? Which is equivalent to finding calculating the Hamiltonian matrix, which is equivalent to calculating all these matrix elements as they are called, okay? And I still haven't told you what these matrix elements are. I will do that in a while. It's pretty much an integral, okay? The Hamiltonian operator is given by this expression over here, okay? Which we use to calculate these matrix elements, okay? And if we use the harmonic oscillator basis, the basis functions are given by this expression. They depend on n. So, and n is an integer that starts from 0. The 0th state is this. and it has this energy. Okay? Sorry, the zeroth state does not have this energy. The zeroth state has an energy of h bar omega over 2. All right, now let's talk about one more thing. So the dimensions of the expression, let's call it xi, equal to the square root of m omega over h. Okay. Okay, let me go. Where do I want to go? Here. Okay. You see that in the Hermite polynomials, the argument inside the parenthesis is x, the position, times this xi that I just defined. Okay. So xi times x should be a dimensionless quantity, because whenever we have physical quantities appearing in functions in physics, they have to evaluate to a dimensionless quantity, okay, so that the function makes sense. Okay, so pretty much this quantity should be dimensionless, but let's go prove it. So to find the dimensions of this, we use the square brackets, which denotes that we are talking about the physical dimensions of this expression. Okay, so okay, now the units of mass is kilograms, the units of omega is seconds to the minus 1, and h bar is joules times second. Okay, and this is to the 1/2. Okay, now 1 joule is 1 kilogram times meter squared over second squared, right? And I messed something up. I introduced an extra second there for some reason. Okay. Let me see. So joules, seconds. So yes, okay, this is the expression I was looking for. I'm sorry. To the 1/2. So this cancels, this cancels. So this has dimensions of meters to the minus 1. So xi has inverse length dimensions. So if we times that with position, we get a dimensionless quantity. Okay, so xi times x is dimensionless. And you probably noticed that sometimes I say xi, some others I say xi. This is because I'm Greek, and in Greek the letter xi is pronounced with xi. Okay, xi is what people, English-speaking people call it. Okay, so anyway, so xi x is dimensionless. But in our case, we will set h bar equal to m equal to omega equal to 1 for simplicity. Okay, though this parameter omega can be varied, and we will see what that does in the code. Okay, we talked about the basis functions a little bit, and we talked about the Poschl-Teller potential in the previous video. So let's go write the Poschl-Teller potential again. So we need to solve minus 1/2 second derivative of x minus lambda times lambda plus 1 over 2 times this hyperbolic second square times psi of x equal to e times psi of x by expanding in the harmonic oscillator basis. Okay, so we know the solutions. Therefore, if we expand in the harmonic oscillator basis, we can directly compare the result we will get by diagonalizing the Hamiltonian matrix with the actual functions that we calculated and we know about, okay? So we need to find, thus we need to calculate the matrix elements N, H, M for the Poschl-Teller potential. Right. Recall, okay, we need to find these quantities over here, okay? And recall that H, the Hamiltonian operator, is given by this expression, -1/2 d squared over dx squared minus the potential, which is lambda times lambda plus 1 over 2 times the hyperbolic secant squared of x. Okay, so again, this is the kinetic energy operator and this is the potential energy operator. Okay, so these matrix elements are equal to this plus this, okay? So let's call this T and M, and let's call this V and M, okay? Now T and M, so this matrix element is equal to this expression, which is equal to the integral from -infinity to +infinity of -1/2, I pull it outside, times the second derivative of Cn over dx squared times the function Cm of x dx. Okay, that's it. This is what that matrix element is. Okay, and the good news is that for the harmonic oscillator basis, there are exact expressions for that, which we will take advantage of, at least in the notes, because in the notebook I actually calculated the derivative, and I will show you. But anyway, so this is the matrix element for the kinetic energy operator, and for the potential, NVM is nothing more than this integral -infinity to +infinity of Cn of x times minus lambda times lambda plus 1 over 2 times the hyperbolic secant squared of x times Cm of x dx. Okay, so that's the other matrix element. Now, in the harmonic oscillator basis, which we will call just HO basis, there is an exact expression for the kinetic energy matrix elements, which are equal to 1/4 times minus the square root of m times m minus 1 times delta of n m minus 2 plus 2m plus 1 delta n m minus the square root of m plus 1 m plus 2 delta n m plus 2. Okay, and this is it, I think, for the theory behind this video. So what we will end up getting is that, okay, this Kronecker delta tells you that T and M will be a matrix that has, okay, actually, let's use indices so we don't get confused. Okay, so 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. Okay, so if this is the matrix representation of the harmonic oscillator kinetic energy operator, then let me see, hope this makes sense, then the only non-zero matrix elements will be in the diagonal, as we will see, because of this term. Okay, so we'll have matrix elements here, and let's say that this is N and this is M. Okay, now this Kronecker tells us that M minus 2 delta N, okay, so delta N M minus 2. So pretty much this matrix element will not be 0, okay, because N is 0 and M is 2. If N is 0, okay, and then this matrix element, because of this element, okay, so okay, let's go to this column, to this row. If N is 0, only M equal to 2 works, okay? That's the only matrix element. If we go to this column, we have N equal to 1. So M minus 2 means that we need 3. Okay, so this matrix element is not 0. If we go to this column, we will have N equal to 2. So only M equal to 4 works. Okay, so this is not going to be 0. If we go to 3, then this matrix element is not going to be 0. Okay, and then this Kronecker delta tells us that if N is, say, 1, okay, then if N is 3 and M is also 3, that's not a 0 matrix element, right? So this element is not 0, right? Yes, so 1 plus 2 is 3. So M is 1 plus 2 is 3. So that's not 0, that's not 0, and that's not 0 either. Okay, so I hope this is not confusing, but these elements and these elements and these elements are the only ones that are not 0 in the harmonic oscillator basis for the kinetic energy operator. Okay, and for the matrix elements of the potential energy operator, we will need to evaluate these integrals, and I will show you how that's done in the notebook. And once, okay, this is just, this matrix is T and M, okay? You also need to calculate V and M, okay? So that you will have the matrix H and M equal to T and M plus V and M. And then you need to diagonalize it. Diagonalize, which means finding the eigenvalues, which will be the energies, and the eigenfunctions, which will be the wave functions, okay, the bound states. And I hope this makes sense. It will make much more sense once we talk about the code. Okay, I will show you in the code how all these come together. I hope this makes sense. Okay, so this is the second way and the most common, pretty much, to calculate the eigenvalues and eigenfunctions of a harmonic oscillator, of a Hamiltonian in the harmonic oscillator basis. Okay, and I'm gonna stop this video here, and in the next video I'm gonna talk about the theory of how you can solve the same problem using machine learning. So if we go back to the beginning of these notes, I hope this is not making people dizzy. Okay, actually I'm wondering if there is a way. Okay, here, sorry, there is an easier way. So I promise that I will show you 3 ways of finding the eigenvalues and eigenfunctions of the Poschl-Teller potential. The direct solution, which we did, So this video discuss the matrix diagonalization way, and in the next video we'll talk about pins. Okay, physics informed neural networks. Okay, and I will stop the video here. I hope this is useful. Let me know what you think about these videos in the comments, and hope to see you around.